Hello, today we study trigonometric substitutions. In my opinion, this is one of the hardest topics in Calculus 2. We will study integrals involving such forms: square root of a squared minus u squared, square root of a squared plus u squared, and square root of u squared minus a squared. And you see how such trigonometric identity works, right? We learned about that already. And let me remind you two integrals involving such forms. The first one is du over square root of u squared minus a squared minus u squared. That is arc sine of u minus a plus c. And second integral is du over a squared plus u squared. That is 1 over a tangent arctangent of u over a plus c. Let me show you how to prove these two integrals, okay? And we'll have some ideas, right? How to solve all the integrals involving these combinations: a squared minus u squared and a squared plus u squared. All right. For the first integral, I put u equal to a sine of theta. So I just consider the interval negative pi over 2 to pi over 2. Okay, we remember the unit circle, right? That is enough to consider, from negative pi over 2 to pi over 2. Because, in that interval, sine will go from negative 1 to 1, right? And the function has inverse. Okay, so I do this substitution. From here I get a squared minus u squared is a squared minus a squared sine squared of theta. Then I factor a squared out. I have 1 minus sine squared of theta. But what is 1 minus sine squared of theta? That is cosine squared of theta, right? So I have a squared cosine squared of theta. Then you apply square root to this function. I have square root of a squared minus u squared is square root of a squared cosine squared of theta. And suppose that a is bigger than 0, so we have a and absolute of cosine of theta. I write absolute because square root of x squared is absolute of x. Don't forget that. But, we consider the case when theta is between negative pi over 2 to pi over 2. On this interval, cosine is always positive, non-negative, let's say this. So absolute of cosine is just, cosine of theta. So I have a cosine of theta. You see, you move from square root to a very simple function. And now you differentiate du, you have a cosine of theta, d theta. Okay, now we are ready to rewrite our integral in terms of theta. You see this integral. So my integral du over square root of a squared minus u squared equal to du is a cosine theta d theta. And here you have a cosine theta. You see, cosine theta, a cosine theta will be cancelled out. So you have just d theta. That is just theta plus c, right? But what is theta? Theta can be solved by using the substitution. So where theta is what? Is u over a, right? You see that? And then you apply the inverse. So, okay, let me write that in detail. From the substitution, we have u over a equal to sine of theta. And then from here, theta is equal to arc sine of u over a. So that's why, this integral is equal to arc sine of u over a plus c. That's how we can prove, this formula. And again, right, in this situation, we do trig substitution. U equal to A psi of theta. The reason we do that because, we want to use this identity. 1 minus sine square equal to cosine square. Because sine square plus cosine square is 1, right? You see, it's pretty nice. Okay, now let's move to the second integral. For the second integral, you see a squared plus u squared. I cannot use substitution, sine or cosine, but I may use this substitution, tangent or sequence. Or basically, I need to do, tangent. Why? Because from this square now, we have tangent square theta plus 1 is secant square theta. And you see, tangent square plus 1 or a square plus u square. You see that? So, for the second integral, I put u equal to a tangent of theta. Okay? Let me rewrite the second integral. Du over u square plus a square. So I put u equal to a tangent of theta. Similar to the case of psi, we consider the case when theta is between negative pi over 2 to pi over 2. In that interval, tangent has an inverse. Okay, so I differentiate this. Okay, let's not differentiate right away, right? I want to work with u squared plus a squared. So a squared plus u squared equal to a squared tangent square theta plus a squared. Again, you take a square out, you get a square tangent square theta plus 1. Or you can write that is a square secant square theta. Okay, it is pretty nice. And then you differentiate du, you get a secant square theta d theta. Now we are ready to rewrite the original integral. That is du is a secant square theta d theta divided by, a square. Oh no, I have a only, sorry. Divided by a square secant square theta. Secant square and secant square will be cancelled out. A will be cancelled out, so you still have one a in here. Okay, so I have a d theta. Again, that is just a theta plus c. So we need to solve, we need to find theta, right? From where? From the substitution. Oh no, I think I do some mistake in here. Here should not be a, it should be 1 over a, right? Because you simplify just 1a. And here also 1 over a. So you solve for theta. Let's solve that from substitution. You have a tangent of theta equal to u. From here you have tangent of theta equal to u over a, and theta is arctangent of u over a. Plus, yes. And then you substitute this into the answer. So your integral du over u square plus a square equal to 1 over a arctangent of u over a plus c. So these two examples are very typical, and that tells you how to use trig substitutions for such combinations. U square plus a square minus u square. Okay, and if you have the combination u square minus a square, so you would think maybe you put u equal to a sequence theta. Why? Because you want to use this identity. Is that correct? Let me write that for you, and then we will move to another example. So when you put u equal to a sequence theta, you have u square minus a square is a square secant square theta minus a square. And you take a square out, you get secant square theta minus 1. What's that? That is tangent square of theta, right? A square tangent theta. So when you apply square root of u square minus a square, you get a tangent theta. Okay. Of course, when you do substitution, you need to choose. You need to choose theta. In this case, you would choose theta between 0 and pi, so that the function will have inverse. Okay. Because sequence is what? Sequence is 1 over cosine theta, and cosine theta has an inverse on the interval 0 to pi, and on that interval tangent is positive. Don't forget that. All right, so I think we are ready with three forming here, right? So let's summarize before we move to detailed solution, detailed examples. So for this form, you have u equal to a sequence of theta, and theta is between 0 to pi. And for this guy, you have u equal to a tangent of theta, and for this you have u equal to a sine of theta. For these two cases, theta is between negative pi over 2 to pi over 2. All right, let's move to another examples with concrete numbers and concrete functions. Okay, let's find the antiderivative of the following function: dx over x squared square root of 9 minus x squared. So you see 9 minus x squared, right? Square root. It seems like we need to apply, the first approach, right? The first formula for square root of u squared minus a squared. Let's say this. So that remind me about, square root of u squared minus a squared. A squared minus u squared, sorry. So for this, you need to put u equal to a sine of theta. If you're already familiar to this, you don't have to repeat this, right? You don't have to repeat the whole process, like a squared minus u squared equal to blah, 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 and you can write finally just a cosine of theta, right? So you can write this directly, okay? We don't need to repeat, the process we just show you. So I have square root of a squared minus u squared is a cosine. So basically I can write, 9 here, right? 9. So this is just 3 because, 9 is 3 squared. And then I put du equal to 3 cosine theta. You see that? D theta. My integral will be, let's say, denoted by I. I is equal to dx. I'm sorry, here you put x, right? Sorry for this. Here should be, okay. Yes, dx. Okay, so you put x equal to a sine. So you have a minus x squared. You have 9 minus x squared in here. So dx is 3 cosine theta d theta. I write 3 cosine theta d theta divided by x squared. X squared is 3 squared sine squared of theta times 3 cosine of theta. You see this? So 3 with 3 squared will be cancelled out. I have 1 over 9, right? Because you have 3 in here, 3 in here, and 3 squared. So that is 1 over 9. Cosine and cosine will be cancelled out. So in the denominator, I have d theta over sine square theta. And we know, sine squared theta is what is 1 over sine squared theta is just, 1 over 9 cosecant square theta d theta. And this is just, cotangent, negative cotangent. Of theta, because the derivative of cotangent theta is negative cosecant of theta. So you have this constant. And of course, the last part is what? We have cotangent in here. We need to rewrite the answer in terms of x. You see? We need to rewrite the answer in terms of x. But we have x is a sine theta. So we need to solve, we need to express cotangent of theta via x. Is that correct? So now we face another problem, okay? Let me write the problem separately. I have x equal to 3 sine of theta. So we need to find cotangent of theta. But I think it is okay. You know, you may find cotangent via cosine, whatever, right? For example, we know that, you know, sine square plus cosine square is equal to 1, right? If you divide both sides by sine square, so you have just 1 plus cotangent square theta equal to 1 over sine square theta. You see that? From here, you get cotangent square theta is 1 over sine square theta minus 1. And if you apply, you know, square root, so you get cotangent of theta is equal to square root of 1 over sine square theta minus 1. Again, you know, when you do this substitution, you would choose theta is between negative pi over 2 to pi over 2. In that situation, you know, cotangent is always positive. So that's why you pick, you know, just plus, right, without negative. Okay, and you know the sine already. You know sine is x over 3, right? So you have square root of 1 divided by x over 3 minus 1 in here. You see? So basically, here should be square. And that's what I have, you know, square root of, I can write in here 9 over x squared minus 1. So I can plug this into this final answer. I will get this is, you know, 1 over 9 with the negative before that, and cotangent is square root of 9 over x squared minus 1 plus c. That's how we can solve this problem. You see, it is long, and I tell you this again, right? Integrals involving trig functions or inverse of trig functions are extremely difficult. So, but the most important is we need to do that step by step. If you see something like this, yeah, try to use the substitution. Once you finish, you know, once you did substitution, you might simplify something, and your function would be very nice like this, and then you can find, you know, cotangent of this. Again, right? You need to solve that. You know, here's funny things. I may write the answer in the following way. Let me copy this, right, without all this, you know, difficult stuff. So I may write in the following way: negative 1/9 cotangent of theta plus c. And again, I have like x equal to 3 sine theta, right? I can solve, you know, for theta right away. From here, I get x over 3 equal to sine theta, and theta is x sine of x over 3. You see? And then I plug theta equal to x sine of x over 3 into this. I get negative 1/9 cotangent of x sine of x over 3 plus c, right? And of course, you know, that is also an answer. Let's solve one example with tangent substitution. In this integral, you see the form square root of 4x squared plus 1. Okay, so that is the form of what? U squared plus 1 squared. And you can find u by solving this. U squared equal to 4x squared. Then u is 2x. Is that correct? And for such form, you know, we know we need to do substitution. U equal to 1 times tangent of theta, right? Because a is 1 in this case. So that is 2x. You see that? From here I have x equal to 1/2 tangent of theta. And that is our substitution. You see, that's how we can decide the substitution, right? Now we just need to differentiate. And I have dx equal to 1 over 2. I can use tangent squared theta plus 1 d theta, or sometimes, you can write 1 over 2 secant squared theta d theta. And you can rewrite your integral. Okay, again, right, we already did that in the second example, but without the square root. So let me rewrite that again, right? For this guy, you have 4x squared plus 1 square root is what? Is tangent square theta plus 1. You see that? Because 1 over 2, when you apply square to the x, right, you have 1/4 tangent square. 1/4 with 4 will be cancelled out, and that is just tangent of theta. Agree? So you have tangent of theta. Oh no, I don't think that you have I think secant square of theta. A square root of secant square of theta, so that is just secant of theta. Okay, now we can rewrite our integral, okay, in terms of theta. Let me write here. So this is equal to dx is 1 over 2 secant square of theta d theta divided by secant of theta. And secant with the secant will be cancelled out, so you have 1 over 2 secant theta d theta. And we know the integral of secant of theta is 1 ln of secant theta plus tangent of theta plus c. So we have, the integral in terms of the answer in terms of theta. Again, we need to solve, right? We need to solve that, solve this, for theta. So I tell you this, right? We can write, as I mentioned previously, from here I can have, 2x is tangent of theta. And from here you have theta equal to arctangent of 2x. So you plug this into the answer, you have 1 over 2 ln of sequence of arctangent of 2x plus tangent arctangent of 2x. Absolute plus c. So what is this? Tangent of arctangent. So that is just 2x, right? In here, of course, you might solve this, right? But again, I'm okay with this answer. Agree? So you see, that's how we can use, this substitution tangent. Okay, let's solve one more problem when you need to do substitution with sequence. So let's consider definite integral from square root of 3 to 2 x squared minus 3 square root divided by x dx. Yeah, you see, there's no way to do substitution like, normal. Even that you have x squared minus 3 and you see dx over x, right? If you have x dx, everything is good. You see, if you have x dx, so you have x squared minus 3, you do the substitution, u equal to x squared minus 3. But in this integral, you have dx over x, so that is totally different. All right, so we try to do, try to use trig substitution. You have the form x squared minus 3. So I can think about, that is x squared minus square root 3 squared. So that is of the form, u squared minus a squared, right? All right, so we do the following substitution. We put x equal to square root of 3 secant theta. Again, right? When I do substitution in definite integrals, I don't want to change the integration limit, so I just try to find antiderivative of the function, and then we will plug numbers into the formula at the end. Okay, so try to do that. From here I have dx equal to square root 3 secant theta tangent theta d theta, and x squared minus square root 3 square is what? Is, I can write here 3. Let's factor that out right away, okay? Secant square theta minus 1. We never did this, right? But I think we showed that before. This is just square root 3 times square root of tangent square of theta, because secant square minus 1 is tangent square. So that is square root 3 tangent of theta. All right. Now I think we are ready. We have dx. We have this part. Now we can rewrite our function in terms of theta, but I just write antiderivative. So I write here square root of x squared minus 3 is square root 3 tangent of theta. Dx is square root 3 secant theta tangent theta d theta divided by x, which is square root of 3 secant theta. What is this? Let's simplify them. We have square root 3 will be cancelled out, so I write square root 3 in here because we still have 1 in here, right? Secant with secant will be cancelled out, so I have tangent square of theta d theta only, which is pretty nice, right? We know this. I think we solved this in the very first lecture about integration, but let's do this again. I have square root 3, so I have to add 1 and then subtract 1, because I know that tangent square plus 1 is derivative of tangent, so antiderivative of tangent square plus 1 is tangent. I have square root 3. That's why I need to add 1 and subtract 1. You see that? Minus square root 3 d theta. So I have square root 3 tangent of theta in here, minus square root 3 and then theta plus constant. So we have an answer in terms of theta, right? Again, we need to solve for the x. You see, we need to solve for the x. So you have x equal to square root 3 secant theta. Let me use in here. X equal to square root 3 secant of theta. So you have oh no, okay, we may solve, let's go back to the x, right? Let's go back to the x. That's what they want to see. Or sometimes if you want, you may change the integration limits in here, and then you substitute new intervals into the function, into this. Let's do that. Let's try that, because in this case, yeah, you have to solve, you have to involve inverse functions, everything. So let's check the substitution. X is square root 3 sequence. Okay, let's write it again. X equal to square root 3 sequence of theta, and in the original integral, x goes from square root 3 to 2. So I can change the following. When x equal to square root of 3, I need to solve for theta, right? So square root 3 equal to square root 3 sequence of theta. From here I have sequence of theta equal to 1, right? Or cosine of theta equal to 1. That means theta is equal to 0. Agree? And then that means the new integration limit is 0, instead of square root 3. When x equal to 2, I have square root of 2 equal to square root 3 secant of theta, or that is square root 3 1 over cosine of theta. From here I have cosine of theta equal to square root 3 over 2. or theta is equal to, let me check that, square root 3 over 2 cosine. So this is around here, so that is pi over 6, I guess. So that is the new integration limit with respect to 2. Then we plug 0 and pi over 6 into this function. Okay, so I have, that is square root 3 tangent of pi over 6, and here minus pi over 6 minus tangent of 0 minus 0. So tangent of 0 is 0, this is just 0, and then we have equal to square root 3 tangent of pi over 6 minus pi over 6. So what is tangent of pi over 6? I think that is 1 over square root 3 minus pi over 6. So you will have 1 minus square root 3 over 6 pi, or this is approximately equal to 0, 0.9 and 31. You see, it is pretty long, right? But you know, that's how we can use trig substitution to solve such integrals. Okay. Of course, you know, as I mentioned, if you want, you can go back from here to the x, right? You can go back to the x. But sometimes we need to find antiderivative, and then you change the integration limits in here, and you will get what you need. Again, you know, the whole process involves a lot of, you know, equations in here. So you need to know how to solve equations with trig functions and then other things. All right. In order to finish this video, let's talk about some special integration formulas. And please copy these formulas for yourself, because we will not memorize, and you know, I don't hope that you will memorize those formulas. They are too difficult to memorize. So you have integral of square root of a square minus u square, and then you know, that is basically 3 basic forms, right? But actually, you know, you see, that is very huge formulas. Of course, we can prove them, right, using trig substitutions, but you know, we don't need to do that. Just accept them, okay? And let's use this one of these formulas to find the arc length of the graph of the function 1 over 2 times x squared from 0 to 1. And you see, sometimes, you know, trig substitutions work really well, right, without formulas. But anyway, let's do this. So, you know, we need to find the arc length. The formula of the arc length, we know that. That is integral from a to b, in this case from 0 to 1, square root of 1 plus f derivative, right, x, and then squaring here dx. Derivative of f is x, pretty simple. So the arc length is integral from 0 to 1 square root of 1 plus x squared dx. You see, the integral looks very simple, right? But you know, in order to solve this, you need to do trig substitution. Okay, let's apply the formula, okay, and then we will do trig substitution. So according to the formula, the third one in here, because you know, integral of u squared plus a squared, this is equal to 1/2. And write here x square root of x squared plus 1, a squared just 1, so I have ln of x plus, I think here should be plus, I think I did something wrong here, plus a squared. So x squared plus 1, okay, and this evaluated from 0 to 1. So at 1 we have 1 over 2 square root of 1 plus 1 plus ln of 1 plus square root of 2. Okay, minus 1 over 2 at 0. This guy is just 0, and we only have this guy, so that is, well, it's 1, so this part is also 0. Perfect. The answer is just 1 over 2 square root of 2 plus ln of 1 plus square root of 2, right? Yeah, that's what we have. Okay, now if we don't use the formula, so how can we do this? If we don't use the formula, we need to do trig substitution. I put x equal to tangent of theta. A in this case just 1, right? So if I do this, I have now dx is secant square theta d theta, and square root of x squared plus 1 is secant of theta. Then my integral looks like, oh, if you want, you can change the integration limits right away. Okay, let's do this, right? Let's change the integration limit. No, I rarely do that, but let's try. For such problems, maybe we need to do that right away. When x equal to 0, I have tangent of theta equal to 0. So theta is equal to 0. When x equal to 1, tangent of theta is 1. So theta is pi over 4. That means, 0 and pi over 4 is the new integration limit, right? So you rewrite your integral. That is, from 0 to pi over 4. And then right here, you have secant theta times secant squared d theta. So you have secant cube theta d theta. And we discussed a lot about such integrals in the previous section when we study secant, tangent, sine, and cosine. You see that? And without looking back, I just write the answer right away. Antiderivative of secant cube is secant theta tangent theta plus ln of secant theta plus tangent theta, and when theta go from 0 to pi over 4. Again, you plug pi over 4 and 0 into the function. Let's say at 0, I think the function is 0 again, because tangent is 0, secant is 1, so this part is 0, this is also 0. So we don't need to care about 0. We just need to plug pi over 4, right? So we have secant of pi over 4, tangent of pi over 4, plus ln of secant of pi over 4 plus tangent of pi over 4. And tangent of pi over 4 is 1, right? Secant of pi over 4 is square root of 2. Okay, so I have square root of 2 plus ln of square root of 2 plus 1. That's what we have. Interesting, we have 1/2. Where's 1/2? Let's see where. Oh, I think we have 1/2 in here. The formula, yes. So sorry, I don't remember the formula, to be honest with you. So that's what we have. Again, two approaches. Actually, the second approach, that is nothing but the first approach. So we use this substitution to prove this formula. So that is no way to avoid trig substitutions. But again, right, this is just an example that show you that sometimes we need to have a formula, a formula tables, integration table, so that we can use them during the course. There is no way to get them, Okay, so I think I finished my video in here. Again, right, this video is long and difficult with new techniques, and each problem has several parts. involving solving equations, everything. So I hope that it is clear enough to you. And again, if you have any questions, please feel free to let me know. All right. Bye bye.